Okay, we have figured out that the chain rule is a big deal. The power rule is right up there with it, whether you're talking about differentiation or integration. Some of this is going to look familiar because we alluded to it yesterday. This U-substitution, talking about in the notes, it's going to make things a lot easier, even from what we talked about yesterday. And using that U-substitution really does help with the chain rule, believe it or not, in all of this. All right. Just a quick review here. Chain rule derivative says what? We've got an inside function, g of x here, and an outside function, f. Well, how do we do the chain rule? We do the outside function's derivative, leaving the inside alone. Chain rule. And then we take the derivative of the inside and just multiply them all together.
So is this like, so are we like, is it the same for antiderivatives? Or?
Except backwards.
Except backwards. So we do the inside first and then
Bless
we
you.
go.
2 times.
So we do the inside first and then we go out.
You'll see. You'll see. Just. Speaking of integration, look what we have to have. We've got to have a derivative of the outside function. And then the derivative of the outside function with the inside function here. And then the derivative of the inside function. This came up in class yesterday that London and Jacob Joseph had argued about before. Okay, if we've got that, then we can integrate it and it just comes out to be this plus a constant of integration. And like I highlighted in green, the trick to this is being able to see, oh, here's a function and here's its derivative in the chain rule sense. Yes, sir?
Doesn't capital F mean antiderivative?
Doesn't what? It can mean anything.
Okay.
It can be the start of a sentence. All right, we good so far? All right, how do we get the antiderivative of a composite function? This is saying pretty much what the last one did, except down here at the bottom, we're talking about the U-substitution. So you take something complex like this up here, you set up U correctly, and you get to this, and then you can solve it a lot easier. And then you can either go back and put the f of x stuff in, or we're going to see you can just leave it U sometimes. Works out pretty nice. Let's actually do a couple of examples. So got x squared plus 1 squared times 2x dx. Again, the trick is seeing, oh, this would be the derivative of something else. And so one clue is look for the more complex thing. Well, that x squared plus 1 to the second power, ding, 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 that's more complex than 2x. So I'm looking at that and I'm thinking x squared plus 1, that could be u. What's the derivative of x squared plus 1? And there's 2x. So if I'm going to substitute, I can say, all right, they're telling us let u be x squared plus 1. That means du is 2x. And there should be a dx out there. That shortens it to something that we see that pattern. U squared du, that's just the power rule.
So is that just x squared plus 1 and we're leaving out 2x, or did 2x go somewhere?
No. This is u to the second power. 2x is the derivative of this. And then the dx is our variable that we are integrating. Okay, so if u equals x squared plus 1, du.
Oh, okay, I get it.
Okay, so then it shortens to u squared du. Well, power rule, what's that going to be?
Du plus 2.
If U was X, wouldn't you just say that? That sounded grammatically incorrect, but it really wasn't.
So what is the
Okay, everybody okay here?
Yeah. Hang on, I'm still trying to figure it out.
Okay, so then what? I can go back and put in what U substituted for. And there's my answer. And that brings up something kind of nice. You can check your answers by just going backwards and differentiating your result. I would probably say, all right, I'll just rewrite it like this. Might make it easier to see. I would say 3 times 1/3, which would leave me x squared plus 1 to the second power rule, times 2x. Yeah? And that's what we started with over there on the left. If you can differentiate your answer and get what you started with to integrate, you're good.
What about the chain rules? Shouldn't the inside be? That is the chain rule.
That is the chain rule. Forwards and backwards.
That's where you get the 2x from. That's the chain rule.
Yeah.
All right, thank you.
And remember, sometimes you can chain along more than just once like this. Sometimes it can get really interesting.
Sorry. So how do you do the
Well, don't be. You're not doing anything wrong, sir.
How do we do the next one? Because it's only x and not 2x.
Let's take a look.
Let's take a look.
All right. So that's the answer we got there. The next one, has du changed?
Yes.
Okay, try again. Has du changed?
Why is it 2?
If
Oh,
u
yeah,
is,
I got you.
okay, all right. If u is x squared plus 1, then du is 2x dx.
Yeah, that makes sense.
Okay. If I'm going too fast, say something. Now what do I've got? I've got this, and I'm rewriting it like this. This is just like the first one, almost, but not quite. So what do I need now? I don't have, okay, let's do this. I can do this trick.
Okay.
I needed 2x dx out there for my du, right? I didn't have it. But if I multiply by 2 on the inside and multiply by 1/2 on the outside, those cancel each other out. Now then I can do my U substitution and say that. Now the 1/2 on the outside stays there because the 2 on the inside is part of the du. And now we're kind of back to where we were before. Just looking at this right here and looking at that one up there, the area of this one's going to end up being 1/2 of the area of that one up there that we just worked, right?
Yeah.
Okay.
Well,
So got this, just like we had before, except for the 1/2. And so that's going to give me this. Which is 1/2 of what we got for the area of the first one. Again, the trick is being able to say, if this is u, what would it need for a derivative? And seeing if that derivative is there. If it's not, sometimes you can manipulate things like I did here. If you can't, then you got a problem, you're not seeing it right. Or it's something that doesn't have anything to do with the power rule or the chain rule. All right, let's keep going. This is just saying substitution is kind of nice. Pattern recognition, we're going to get to more and more, and that's not as straightforward, I don't think. Okay, we're going to integrate this. What would you say U is?
Is it x squared minus 1?
Is it 2x minus 1?
Or sorry, 2x minus 1. Or,
That's what I would call U,
and
is
so
2x minus 1. That makes du this, right? Oh, stop. All right. If we differentiate 2x minus 1, we get 2 dx. Now, I left a little gap in there between my square root of 2x minus 1 and the dx. Why? Now, there's not a 2 there.
Right.
So I do that trick again. Now then, I can look at that and say, okay, I've got u to some power du. So I've got that. Which then, when I integrate that, becomes 1/2 times u to the 3/2 power divided by 3/2. Now, one trick is you can take that denominator and just flip it and multiply it by it, right? It's a version of keep, change, flip.
Wait, where did the 3/3 come?
I took the denominator of my u to the 3/2, flipped it over and multiplied by it.
Keep, change, flip.
Now the 2's cancel. So I've got 1/3 u to the 3/2.
Now we put u back in as 2x minus 1.
That's right. We can go back and unsubstitute, if you will. So it behooves you to keep track of what u stood for. So write it down.
Huh. Okay then.
When you see about 20 or 30 of these, you're going to go, oh, that's easy.
Yeah, I see. I'm seeing all the pieces, and all the pieces seem pretty easy. I'm just putting them together.
This is brand new. This is brand new. Until you get to calculus, you might get a glimpse of some of this, but you don't really know why. We good on this one?
Yes.
Guidelines. This is saying choose the inner part being raised to a power. Okay, yeah, I agree. I mean, we just did all of these things. Let me add to that. Look for the more complicated thing. That's usually where you're going to find the outside function. I think that'll hold true, if not all the time, at least most of the time. Okay, this is in your notes. Look what they're doing here. The top part up there, g to the x raised to some power times g prime of x dx, that's just the basic, yeah, just basic integration. But if you can get a U-substitution going on, notice it's just like it. Just exactly like it. Okay, let's look at one here. All right, thoughts. What would you say U is? I agree. Now, let's write that down. What's du then?
3 will be
Nearly.
3 to the 4th power.
Nope.
That's just the
What's the derivative of 3x minus 1?
3 plus
Dx.
the.
That was a collective. All right. Do we have that sitting in front of us?
Yes.
Yes, we do. Now then, y'all, when I made up these notes, I rearranged things so it would look like, okay, like this. You don't have to do that. What I did was I put the du sitting right there, and that's du. And this is u to the fourth. That's why I wrote it like that. You don't have to change the order if you can see it. All right, so then I've got u to the fourth du. A lot simpler. Now what do we do? Integrate. Uh-huh. Yeah, technically the C ought to be there, you're right, but I'm just saving it for the end. Just don't forget it is the main thing.
Oh yeah, you forgot.
That was hurtful. That was hurtful.
Oh yeah, you did forget one.
Thank you all for joining in the beating. Okay, can we keep going? Let's look at B. Yeah, I feel the love in the room. What would you say U is?
It's x squared plus x. Wait. Oh yeah, it's the most complicated thing.
That's a good guideline. So, if that's U, what's du?
It's 2x plus 1.
Nearly. There you go. And again, we've got that sitting right in front of us. A lot of math, I don't know if you've realized yet, is just patterns. Okay, so that ends up with just u du. So when we integrate, I get that, which gives me that.
It's clicking.
Good.
It's actually not too bad.
This is not too bad.
I'm clicking too, but instead of the normal clicking, it's just me. It's just my head spamming the pen clicking. It's just,
So it's a substitution of clicks. Again, let me reiterate, if we took that last thing, x squared plus x to the second power over 2, and got the derivative of it, we should end up with what we started with. All right, let's look at yet some other stuff. Oh, we got another one of these. What would you say?
x to the cube minus 2. X to the cube.
X cubed minus 2? That'd probably be a good u there.
Yep.
And notice the thing that I highlighted back there where it was giving you the pointers was that's inside something.
Your d is inside something?
What's inside of the radical in this case? Okay, what's the derivative of u cubed minus 2?
3x squared dx. Oh, 3x, right.
Exactly.
We're clicking this your left.
I can hear it.
I think I did it right.
And so again, just to make sure everybody sees the pattern, I just changed the order. That's all I did right there. Didn't have to. If you see the pattern, if you look at C up there the way we started and you see the pattern after you write down what u and du are, then you don't need to change the order like I just did in that part right there. All right, so I can change that to u du. Much simpler to work with. Now what?
Now we integrate it.
We do, and so what does that exponent become?
U to the 3 halves over 3 halves plus c. Or 2 halves over 3.
Or if you take the denominator and flip it and multiply, you get this.
If you're fancy.
Yes. And then you can go back and do this. And you're done.
That's minus 10. This feels too easy. I feel like I have to.
Careful what you wish for.
Why would you say that?
That's what General Custer said.
Oh, please.
I'm not arguing with you. You can do all of this. Ooh, what would you say U is here?
1 minus 2x to the square.
If that's so, what's du?
X minus 2x to x. Minus 2, minus 4x dx.
Are you having an aneurysm?
Yes, mine's 4x.
Now then, here's the trick. Is that sitting in front of us?
Kind of. Yes, it is.
Yes, it is.
It's to the minus 2 is u to the minus 2 times du.
Notice the negative 4x is not sitting right by the dx, but they are technically being multiplied because negative 4x is the numerator, right? So another way to visualize it's like this, right? Just like Jacob Joseph said. So now I've got just a power situation. At the risk of repeating myself, the trick is seeing the patterns. All right, so I've got that. Big area of mistake here. Don't go, okay, so u to the minus 3. We're adding 1 to negative 2. That's got to be one of the most common mistakes. And so then I've got this. So all that complex thing simplified to negative u to the negative 1 power. And you can rewrite it like that if you want to, which gives us that. All right, which brings us to B. The more complex thing is the cosine squared. So what's being squared? Cosine x. Okay. That's different from cosine of x squared. Cosine parentheses x squared. Okay. There's a huge difference there. All right. So I'm going to say u equals cosine x, just like you all are suggesting. What's du?
So why did you cosine squared and not?
So would you have to take out a minus half?
Not necessarily half.
Well, doesn't it have to be 2? Because it's squared.
Well, no, don't get the u part confused with this part. So here's what it's going to look like. I left a little space here in front of my sine x dx because we don't have the actual du yet. I need a negative sign in front of that sine x, which means I need one out front. Those two negatives would cancel each other out and give us what we started with. And if you look at other instructors, they might explain that a different way. I don't think this is a bad way to explain it. They just cancel each other out. Now I've got a u squared du. As long as you don't forget the minus sign in front, it stays. This is actually one of the more fun parts of calculus, I think. It's just like solving little puzzles. All right, so then I integrate, keeping my negative sign. And end up with that.
Plausible.
Isaac Newton thanks you. All right, questions about those two? We're good. All right, let you read this for a second. Might not seem crystal clear at first blush there. What have we been doing? We have, Now look, we're talking about definite integrals here, where we're going from something to something. Everything we've been working with so far in this set of notes is indefinite integrals, which is just a generalized case. That's why we've got that plus c out there. But now we're talking about, oh, I want to go from a to b in this integration. This is just saying, if you do a u substitution, and that u is substituting for some g of x, then you could leave things in the u form, and the lower bound is going to be g of a, and the upper bound is going to be g of b. It's just a translation kind of. Let's look and see what they're talking about. This says do this two different ways. So let's do it the way we've been doing it. So looking at that, what would you say u is?
X squared plus 1.
All right, I agree with you.
Really?
Yes. What's du?
2x dx. To the power of 1. Dx.
Do we have that sitting in front of us?
No. So
No.
I have 1 half of it. Oh, so that's how.
I need a 2 there. That means I need a half outside. Now we're getting it in the form of a u substitution. And so I can do this. Very simple. Think about how far y'all have come in this. It's an amazing distance in a short time. It really is.
I mean, I've gone from not understanding this at all to understanding it.
But understand this.
What a concept in education. All right, so I've got this. Now what do? I got to keep my half. Nope. And I can go ahead and multiply by half and get this. Pretty simple. And then I can do what? I can unsubstitute. But now look what I'm doing. This is a definite integral, so I'm going to integrate from 0 to 1.
I thought you had to put it in the function.
That's our antiderivative that we're evaluating.
No, yeah, for like.
We're going to do this two ways. This is the way we've been leading up to with all those indefinite integrals. So this is way number 1 that you could do it.
But doesn't it say here that g of a and g of b?
That's way number 2. You've got to read between the lines here, Jacob Joseph.
Or just in general. I haven't read it.
All right, so now what am I going to do?
Plug in 0.
Start plugging stuff in. So I plug in my 1s first. So I've got 1 squared plus 1 to the 4th minus 1.
Which is 1.
Well, notice where I got the 1. It was really what? 0 squared plus 1. The 1 right there on the end came from 0 squared plus 1. Okay. We're just down to numbers now, which gives me 15/8. Notice no constant of integration needed. The area under that curve is 15/8. Exactly. That's one way you can do it, where you get a u substitution, you work it out, you go back and replace u with what you substituted it for and evaluate that. Now notice the 0, 1 are constants.
Would we have to subtract the lower one if it wasn't 0? Because we have to do it with 0, right, too, but it would be.
Yeah, you'd plug the lower one in and whatever you get there, subtract it. Yep, good question.
Don't forget about my recommendation later.
I will not. All right, the other way of doing it is to say, all right, g of x equals this. right? And you might say, well, wait a minute, what about that x up there? Well, that x is really part of the derivative of gx. So don't get confused. G of x is really x squared plus 1. And so I can evaluate it. Look where I'm evaluating it, at the limits we started with. So g of 1 is just 2. And g of 0 is just 1. Okay, so I can do my U-substitution. And look what I'm doing. I'm just saying right there's where I did the U-substitution. But look what I'm doing there. I'm plugging in the g of 1 on top and the g of 0 on the bottom. This is what that set of notes was talking about. You might just want to leave it u. You just have to change your limits of integration. Now, theoretically, we should get the same thing. We should get 15/8. So notice what I'm getting here. Is this any different from what we had before? I haven't gone back to substitute my x function in. I'm just leaving it u. Evaluate from 1 to 2. Our original setup was evaluate from 0 to 1. But if we just leave it u, it's going to go from 1 to 2, because at the risk of over-explaining, that 1 is g of 0, which was our original lower bound. And the 2 is our original upper bound, 1, run through the x function, the g function. All right, so I do this. And look at that. Same. So there might be times you just want to do it this way. Dealer's choice. Heck yeah. One last little thing. We talked about even and odd in pre-cal. If I get to do this next year, I won't be able to say that.
That's true.
Y'all are my last pre-calers. I bet you Noel's covering it. Okay, so even and odd. Look down at the bottom. An odd function is what? If the y value, f of x, equals negative the y value for negative x. If that's true, that's symmetric about the origin, right? A perfect example is the cube, y equals x cubed. I could spin that thing around and it would lie on top of itself if I spun it 180 degrees, right? Around the origin. Look what an even one is saying. If f of x, if y, doesn't change if you put a negative x in there. And think of a parabola with the origin as the vertex. Those sides with the y-axis as the axis of symmetry, those sides are equal. So look what this theorem's saying. If you've got an even function and you're going from negative a to positive a, then really all you had to do was just go from 0 to a and multiply that by 2, because 0 to a would give you half the area. As long as you've got an even function. If you do the same kind of thing with an odd function from negative a to a, you get 0, because part of it's positive, part of it's negative. The part below the x-axis is negative. They cancel each other out. Again, the trick is recognizing that situation. What's going to give it away? Well, the negative a, positive a thing. If those numbers were different, if it was like from 3 to 8 or something, or from -3 to +8. Then that doesn't matter. Because this depends on what? The origin or the y-axis symmetry. Yeah. Okay, so let's look at a couple. Hot dog. Trig. Now notice it's going from -π/4 to +π/4. There's the little signal that, oh, maybe we better look for odd or even. So we better check. So I ask myself, does cosine x equal negative cosine negative x? And you might be going, well, how would I know? You have to remember cosine of negative x, doesn't that equal cosine of x? If you think about a unit circle? Because cosine in quadrant 4 is positive. So that's not true. Cosine x does not equal negative cosine negative x. So I know it's not odd. And so then I ask, okay, does cosine x equal cosine of negative x? And the answer is yes. Any place on the unit circle, that's true. So it's symmetric about the y-axis, you're right. So I can just integrate from 0 to π/4. Now, what if you didn't catch this? You'd work the problem, you'll get the right answer. It might kind of catch you off guard if the area is 0. That might be a tip-off that, oh, wait a minute, the negatives cancel out the positives kind of thing. So what's U here? Mm-mm.
Is it cosine of 2x?
Nope. It's 2x. That's the inside part. This is different from cosine of x. This is cosine of 2x. So U is 2x. Du is 2dx.
What's the cosine of it?
Well, let's take a look at it like this. So I've got this. I just rewrote it. What's the antiderivative of cosine? Sine. Watch out, don't put a negative in front of it. The derivative of cosine is sine. The derivative of sine is negative cosine. Weird. Okay, so I've got sine of 2x evaluated from 0 to π/4.
Do we throw U in?
Oh, U is gone. So if I've got π/4 times 2, isn't that just π/2? If I plugged up π/4 into sine 2x, wouldn't I have sine of 2π/4? Everybody seeing? Okay, so I've got sine of π/2 minus sine of 0. Well, what's sine of π/2? Okay, there's a difference. It's 1. And the sine of 0 is 0, so the area under that curve is just 1. Now, did it bother anybody that the 2 that started off in front up there in the blue disappeared?
You moved it in.
I moved it in.
I did see that, that's fine.
Yeah. Yeah, I just didn't color it in red. That 2 that was on the outside became our du2 on the inside. Okay, let's try one more.
This one's gonna end up being 0 because it's on.
Okay, we ask ourselves. Now we're cubing something. So yeah, that works out. So I'll say u is sine x, du is cosine x dx. Boom. Nothing to work out.
Thank you, Mr. Ladley.
You bet. I enjoy this with y'all.
I feel like that